My name is Celine, and I'm extremely happy to be part of this event because essentially it's a worldwide event which happens in every country, and it's all about thinking. When you think, you actually think differently depending on nationality, depending on the language you speak. And so what I want to show you today is some of the things which actually is a blind between the way the English speak and the way the French speak. It would be nice if actually slides showed now. We have, here we go, and we can go to the next one, thank you. So, the title of this event is actually The Elephant in the Room. And in English, this means there's something there and you don't necessarily speak about it, but you know it's there. In French, we don't have elephants in the room, it doesn't exist. There's nothing that we didn't speak about, right? We have something very important, which is actually from the Bible, but we have a sentence, which is, I'm like St. Thomas, I only believe what I see. So, which means that you can only do things if you've seen them. If you didn't see them, like elephants in the room, then you can't go anywhere. So this sentence is actually very important for scientists, because it is actually at the basis of any work, any research work. Any scientists have to basically provide hypotheses and test them. And to test them, they have to provide evidence, and those evidence have to be unambiguous. They have to convince not only themselves, but they have to convince everyone that they're correct. So for that, they have to bring things that everybody else can see so that they can judge that the person is correct or not. And so typically, for example, I could tell you, well, in English, you have elephant in the room, but I don't believe that because I don't see them. However, recently, I have seen an elephant in the room. It was extremely big. It was actually even bigger than the normal elephant you think about. And not only that, but it was all in wood, and it was walking. Now, at that stage, you actually laughed because, it's not. This doesn't exist, right? This is only a French thing. You should be right, but I'm in it, and I can prove it, and the way I'm going to prove it is to show it to you. If it works, and it didn't. Okay, but can you just press so that the film shows, if it works? So this is my elephant. What up? It was before. It was not working anymore. Okay, well, whatever. It's okay, we will survive. So you see, this is an elephant in the room. There is a roof. It's in the room. It's an elephant in wood. It was very big. The video was fun because eventually you see the elephant spits on me. Not only walks and moves his ears, spitting on me at the end. So there are elephants in the room, and I have seen one. So being French, I can tell you, yes, now I believe. Right? Now I will move the transparencies. Okay, so the question is, to convince people, you have really to bring evidence. But what does it mean that, you see? How do you see things? And if you're a researcher, it depends on the field you are. So for example, if you're an astronomer, you can actually see things by looking at the sky. So if you see basically a star, you see a bright light coming to you, then you can say this is a star. But it's only visible light come to you. In some cases, we can still see objects in the sky, even if they don't emit visible light. They can emit some other type of light. They can emit some X-rays. They can emit some gamma rays, but you don't necessarily see them with your eyes. What you need, though, is a specific type of detector, which in astronomy is a telescope. Now, if you're a particle physicist, you try to see something which is even smaller than a proton or than an electron. How do you do that? Well, you can still see things, you can still see those particles, because you can smash hydrogens, basically ions, and then you build this detector so that the product of a collision between two atoms gives some charged particles, and the charged particles, the fact that they're electrical charge, will bring some lights in the detector you can see. And this is exactly what people use, for example, to detect the Higgs boson. what you can see, if I manage to show you, you have tracks here, which are, oops, you see tracks from the boson decay into charged particles. So they deposit energy, they deposit light. You don't want it anymore, okay? Okay. So if you're a particle physicist, you have means to see events, and you can see them straight. Can you go back? Thank you. And you can see straight, basically, as a picture on the screen. Now, of course, this is if you're a physicist, but if you're a biologist, works for a biologist, you can show, for example, that the human can attack cancer cells. And the way to show this is to have a picture. See that this is true. But this picture, you get it through a microscope. Thank you. So the thing is, now we've seen things and we could show to the rest of the world. And this is the way science has progressed until now. But in the last, people have realized that actually sometimes you don't see things. There are elephants in the room. And actually, it's not in the room, it's in the universe. And we started to realize that there are, but which are there. And so, in particular, there's something extremely interesting, which is if you look at a spiral galaxy, so you can see here, is constituted of a bulge, and then you have spiral arms. Now, if you look at the stars, and you look at two stars in particular, one very far in the spiral arm, and very near the galactic center, very near the bulge. You look at the way they evolve, and you look at their rotation velocity. What you see, and what you would expect first, a star which is very far from the galactic center, the one which is in the spiral arm, should have a rotation velocity which is much less than the one near the center. So if you can't really understand why, imagine yourself in your bath, and then you plug the thing for the water to go out, and then you see that the foam particle behind you should go not as fast as the one very close to the tube. So it's exactly the same principle. There should be dissipation, and the star very far from the galactic center shouldn't have the same velocity as the one near the galactic center. And guess what? We've done the experiment, we've looked at many, many galaxies, and everywhere stars very far away from the galactic center, they go exactly at the same, they have exactly the same rotation velocity as the stars very close to the center. In other words, in the galaxy, there is no dissipation. And this is not what you see on Earth. So the question is, how do you explain that? There are several explanations, but the one that the community in general accepts is the fact that there is a lot of invisible matter all around galaxies. And so the current picture is that you see something bright because it's full of stars. It's in a galactic disk, it's full of stars, and it emits light. Around, you have a halo of invisible matter. Now, this halo of invisible matter exists in galaxies, but you could tell me, well, is there any other counterpart of it? Can we see it anywhere else? And the answer is yes, we can. We can see it at different scales. And in particular, we see it in clusters of galaxies, so all galaxies together. And then what we see is even better, because what we see is that this invisible matter is so present that it actually curves the light to us. Now, clusters of galaxies, we see them, we study them. But what is kind of a miracle is that I can now tell you we know invisible matter was present when the universe was a baby. So when the universe was 4,000 years, there was this invisible matter. It was there, it was present. And the reason we have two experiments which actually picture this, which is the distribution of light and matter in the early universe. And those two experiments, WMAP and Planck, told us that there are big regions of space which are hot and other regions of space which are cold, but there are also small regions of space which are hotter than others. And without the invisible matter, we wouldn't be able to describe this. Now the thing is, what is now absolutely astonishing is that this invisible matter connects us all. All galaxies are related with each other through this invisible matter. And what is two simulations of the our prediction based on our knowledge of what the universe looks like. The person who's done the simulation is Yashe. He was a former PhD student in Durham. What is amazing is that we don't know which universe is correct. And yet, seeing the structure in filaments, we know they are. We know that our predictions are correct, which how much filaments there are in the universe. Now, this is extreme. This is probably ruled out. Something in between is actually possible, and we're thinking of which universe we live in. So, this thing is incredible because you have some invisible matter all around us. It's there. It's helping to form all the objects we live in, but at the same time, it's connecting everything in the world. So it's like a network. It's building a network. And the question is, what is it? And we have no clue. So I can tell you a lot about it, but I don't know what it is. But if it is, then perhaps it is a particle, in the same way as you have electrons and protons. If it is particles, then I know things because I don't see it, so it doesn't have an electrical charge. It's basically, it feels gravity, so it has a mass. It was there before galaxy formed, so it's extremely old. It's still here, so it's stable. So I know a lot of things. But if I compare all the particles I know and that we found, so what we refer to particle physics, in particle physics, then I know the particles we know actually have those properties. So if it is a particle, it is actually a new type of particle, which means that if we found the matter, if we can, we may actually show a new type of particles, but also a new type of forces in the universe. And those forces may reveal something even bigger than what we think so far. So the thing is, I'm just going backwards once before I show you the film. The thing, we don't know, but we know how it doesn't interact with us. And the reason is that if it interacts with us too much, we would destroy the code. And we know that it's not the case. And I'm going to show you a film to show you I don't know what is this invisible matter, what is this dark matter. I actually know how it interacts or how it doesn't interact. And so here's the film. You see the filaments I told you about. This is the whole universe as we picture it. Filaments cross, you have galaxies and clusters of galaxies. Now we're going to zoom in a Milky Way, basically. And you see many, many little small structures, what we call companions, which are just dark matter lumps, invisible matter lumps. And those are small galaxies. Now on the right, and you will see it clearly, this is what happened if a dark matter was interacting with the ordinary matter. And it means also even with particles which are neutrinos. And now in a second, what you're going to see is what happens if the interaction was too strong. And if the interaction is too strong, what is amazing, suddenly the Milky Way is completely stabilized. You wiped out all the little structures in the Milky Way. But we know it's not the case. We've seen them. We've seen that the Milky Way contains small galaxies inside it, and we call it the. So essentially, even though I don't know what it is, even though there is an elephant in the room, I can tell you what the elephant is doing. And that is absolutely amazing. So to conclude, well, we don't know what it is, but we know this is going to be absolutely amazing. This is going to be a revolution in understanding the world we live in knowing actually what are the principles, the fundamental principles, elements of life. And so, for example, it could be a new particle, a new type of forces communicating to our world. It could be primordial black holes, which formed just after the Big Bang. It could be actually extra dimensions. Extra dimensions mean a different universe communicating with us through gravity, and you would see the manifestation as dark matter. Or it could be actually the fact that we didn't understand anything about the nature of the universe. It works, we can predict some things, but maybe we see the tip of the iceberg. So we know there is an elephant in the room, so the British are correct to use this word, there is an elephant in the room. But what I do is that you will never believe me until I show you evidence, proper evidence. And so we all have to be French on that one. We have to be like Saint Thomas. We need to see and find the proper evidence that we can picturize to be convinced. Thank you very much.